Hello everyone, and in this video we're going to continue our discussion of limits, and we're going to be looking at if a function is continuous at a point. So in pre-calculus, you might have seen the phrase, you can draw the graph or make the graph without lifting your pencil or pen. And that's referring to a function being continuous or not. If you can do that, the function's continuous, but that is not a genuine mathematical definition of continuity at a point. That's just a phrase. That's just a phrase I wanted to bring up. Sometimes you hear that in previous math classes. A more concise definition is a function f is continuous at x equals a. A is just some constant, some random point. If the following three conditions are met, first of all, the function has to exist at that point. So f of a has to equal some value. There can't be a hole or an asymptote right at that point. Secondly, the limit as x goes to a of f of s or of f of x must exist. So if the limit from each side does not equal each other, then the limit doesn't exist, and we discussed that in previous videos as well. So the limits have to equal each other from both sides for the overall limit to exist. Thirdly, f of a must equal the limit as x goes to a of f of x. We touched on that in a previous video as well, where just because the point, or just because the limit exists, that doesn't necessarily mean that the point will exist at x equals a. Now, when looking at the example problems, we need to look at argumentation, like mathematical argumentation. You're going to be arguing, okay, if it's not continuous, then you have to prove that. If it is continuous, then you also have to show that. So if at least one of the criteria is not met, the function is discontinuous at x equals a. And if the function is continuous, you must list all of the criteria. So you have to argue all three of the criteria. Why is it continuous? So let's say the function is continuous and you missed one of those criteria. Well, then it's like, okay, is the function discontinuous at that point, or did you just miss one of the criteria? You have to miss all that, make all that criteria known if it is continuous. If the function is discontinuous, then you only need to list one, or you can list all of that criteria, but you only have to list one, because all of the criteria has to be met if the function is continuous. If only one of it's not met, then it's discontinuous, and that's an appropriate argument to be made. So we can look at some examples here. The first question is, let f of x equal the square root of x minus 3 over x minus 9. Is f continuous at x equals 9? Say why or why not with proper justification. So first of all, I'm going to try to list if it's discontinuous, I'm going to try to list all of the criteria just to help make it more obvious, help you out. But note that you only have to list one. So we're going to plug in 9 right away. So f of 9 equals the square root of 9 minus 3 over 9 minus 9. And then that's 0, and then that's 0. That's 0 over 0. So f of 9 does not exist. So we could be done right there. We could really be done right there and say at x equals 9. We could say f is discontinuous. I'm just going to write discont because I want more room. At x equals 9. And then there's some symbols in mathematical argumentation that you might want to know. I'm going to use those symbols because it's appropriate to get, it's good to get a feel for the notation. So the mathematical symbol for because is those 3 dots right there. So you don't have to write that. Like none of your teachers, or I'm not going to be that picky if you just write because or the 3 dots. It doesn't matter. It's just another way of writing because in math. So f is discontinuous at x equals 9 because f of 9 does not exist. Okay. And that would be good. That problem would be done, and that is a good justification. But if we want to keep going, we could list all of the criteria. And that's what I'm going to do. But note that what we have now is a good justification. So I'm going to do the limit as x goes to 9 of the square root of x minus 3 over x minus 9. This equals the limit. And since I don't have enough room, I'm gonna take a shortcut here. At the bottom of the fraction, the denominator, notice how this is technically a difference of 2 squares. Because you're taking the square root of the first term and then the square root of the second term. It doesn't have to be an even power to take the square root. Like that. You can take the difference of squares of that if you want, because you're just taking the square, that's a 1 right there. You're just taking the square root of x to the 1, which is the square root of x, and then the square root of 9 is 3, and then you have a minus and a plus. So that would be a difference of 2 squares. But you could use use multiply by the conjugate, but this is just another way of doing it. So I'm going to cancel the square root of x minus 3's, and then I'm going to plug in the 9 right away. The square root of 9 is 3, plus 3 is 1/6. So now I could say f is discontinuous at x equals 9 because f of 9 does not exist. And then I'll say, and the limit as x goes to 9 of f of x does not equal f of 9, because you can't equal something that doesn't exist. So the justification, I'm going to erase all this limit stuff. The justification is the f is discontinuous at x equals 9 because f of 9 does not exist, and the limit as x goes to 9 of f of x does not equal f of 9. Notice how you don't need this justification, really. You could, if you want, you only have to do this part, because you only need one reason why a function is discontinuous. But yeah, sorry, I'm just trying to emphasize that part. But yeah, okay. Now we have another example here. Let g of x equals sine squared of x over tangent squared of x. Is g continuous at x equals pi over 4? Say why or why not with a proper justification. So immediately what you want to do is you want to find what the function is equal to at that point. Or I'll write it up here if that's all right. So g of pi over 4 equals sine of pi over 4, that's squared, over the tangent squared of pi over 4. Tangent of pi over 4 is 1. 1 squared is 1. The sine of pi over 4 is the square root of 2 over 2. So if I square that, I'm going to get 2 over 4. and then that's 1/2. So that we know f of a does exist. F of pi over 4 does exist. So now we're going to find the limit as x goes to pi over 4 of g of x. And there's no real discontinuities at pi over 4. I mean, we just plugged it in. We just plugged in pi over 4 up here, so we can also say the limit is 1/2 because there's no discontinuities at pi over 4. So now our justification, we need to recognize g of a equals the limit as x goes to pi over 4 of g of x. So the limit and the point are equal, so we can say f is continuous at x equals pi over 4. And then I'm using the because notation, but you don't necessarily have to. F is continuous at x equals pi over 4 because f of pi over 4 exists the limit as x goes to pi over 4. Oh, and this is my bad. This is the function is not f, it's g. I apologize for that. That's another thing. You want to make sure you're using the correct function. We usually use f of x as the function, but sometimes it'll be a different function. The limit as x goes to pi over 4 of g of x exists, and g of pi over 4 equals the limit as x goes to pi over 4 g of x. So g is continuous at x equals pi over 4 because g of pi over 4 exists, the limit exists, and they're equal to each other. And then I'll write 1/2 equals 1/2 just for further specification. So now we have our last problem here, and I wanted to make this a graph to make it really get it more skills, show different representations. So let h of x equal 3 over x minus 3. Sketch the graph of h on an interval of your choosing. Is h continuous at x equals 3? Say why or why not with proper justification. So I'm going to draw a graph here. Hopefully you know how to graph this from pre-calculus or algebra. So there's an asymptote at x equals 3. That's what the graph will look like. Hopefully you memorize this type of graph by now. And I'll erase a bit of that right there. So that's what roughly what the graph will look like. It's just a sketch, so it doesn't have to be perfect, and you don't necessarily have to list points. But I just wanted to also sketch a graph so you can recognize what continuity would or would not look like. So let's see. Let's plug in the point. So h of 3 equals 3 over 3 minus 3, which is 0. And that's 3. So does not exist. So at x equals 3, h does not exist. And then we could be done right there, but I'm going to keep going just to show you what it looks like with all the reasoning points. So let's find the limit as x goes to 3 of h of x. Now, notice how I said at the beginning of the video that the limits from both sides must equal each other, or the limit doesn't exist at all. So, you're going to a y value of negative infinity, and then infinity up here. So the limit is going to different values. So we can say this limit, I'm going to get rid of that equals sign. This limit does not exist. So now we can provide our reasons for why. Hopefully you can see this is discontinuous at x equals 3. So h is discontinuous at x equals 3 because h of 3 does not exist. The limit as x goes to 3 of h of x does not exist, and h of 3 does not equal the limit as x goes to 3 of h of x. You only have to list one of those criteria, but I am listing all of them for clarity's sake. And that should be the end of the video. Thanks for watching, and if you have any questions, please leave them in the comments. Thank you.